Today my topic for the presentation is stability of nonlinear control systems. The main objective of this topic is 1. What is the difference between linear and nonlinear control systems, and second one, what are the possible methods of stability of nonlinear control systems. So coming to the definition, difference between linear and nonlinear control systems. A nonlinear system which does not obey the principle of superposition and homogeneity is called a nonlinear system. Whereas in the linear case, it obeys both principles of superposition and homogeneity. And also, if you take a spring mass damper system, which is a linear system, suppose if you add a nonlinearity to that system, automatically that becomes a nonlinear system. So, in the example 1, we have given the mathematical equation of spring mass damper system mx double dot plus fx dot plus k1x is equal to 0. It is a linear system, but we have added one non-linear term to that equation. Automatically the system becomes a non-linear system. Means here we added one non-linear element to that spring mass damper system. Similarly, example 2 is also an example for non-linear system. So the difference between linear and nonlinear system is that one just now we discussed, it does not obey the principle of superposition, and also the response of nonlinear system to a particular input signal is no guide. Means its responses cannot be predictable and highly sensitive to input amplitude, which is not happen in the case of linear systems. And also stability depends on the input and initial state. It also exhibits a special characteristic called jump resonance and limit cycles, which are self-sustained oscillations of fixed frequency and amplitude. And also one more characteristic is that the unexcited stable linear should eventually come to rest. These are the differences between linear and nonlinear control systems. Coming to the stability, first we will see what are the possible ways of conditions for the stability of linear systems. So when we are deciding the system stability in linear systems, mainly we will focus on location of system poles, and second one is that the stability of undriven linear system is independent of the magnitude of finite initial state, and also stability is very much dependent on the input and also on the initial state. These are the considerations we will make when we are deciding the stability of linear systems. Coming to the nonlinear system, the main considerations for the stability of nonlinear system is that one is, as we discussed, limit cycles, which are self-sustained oscillations of fixed frequency and amplitude, and another one is jump resonance. So if you see an example for a linear system, just now we discussed spring mass damper system, which we are showing you as a diagram, is the example for linear system. For that one, if you add a nonlinear term of k2x cube, the characteristic automatically becomes nonlinear. Suppose if the term that is not there, then the characteristic is linear. So suppose if it is a hard spring, then k2 is greater than 0, and the characteristics of force versus amplitude becomes like this. As the amplitude increases, force increases. Similarly, if it is a soft spring, then the characteristics will be like this. So these are the non-linearities that is exhibited by the system. So this type of system is called non-linear system. The main stability methods of non-linear control system is that one is phase plane analysis, another one is describing function approach. In the phase plane analysis, we will construct the number of phase trajectories from the family of phase trajectories, which are also called as phase portrait. We will decide whether the system is stable or unstable. Here, for each and every initial condition, there is a phase trajectory. Based on the number of initial conditions, number of phase trajectories can be constructed from the phase trajectories, and from the concept of equilibrium, we can decide whether the system is stable or unstable. Suppose if the system is converges to the equilibrium state, then the system is a stable system. Suppose if it is diverges away from the equilibrium state, then the system is unstable. In this way, we can decide the system stability of nonlinear system by using the phase plane analysis. The main advantage of this method is that it is easily constructible, and also it will give the graphical picture of the total system response. But the main drawback of this approach is that it is limited to first order and second order systems only. Practically, most of our points are more than second order systems. So this method of stability may not be useful at all times. So next method of stability in nonlinear system is describing function analysis. In the describing function analysis, we need to make certain assumptions which are listed here. After making these assumptions, we need to frame the describing function. Well, the kn of x comma w is equal to ratio of amplitude of output, nothing but response, to the input amplitude with its phase angle considerations is called a describing function, and the response is given like this. So here this mathematical formulation can be done by using Fourier series analysis. So after doing the Fourier series analysis and finding the functions a1, b1 and everything, we will finally frame the kn of x comma w as y1 by x at an angle of y1, where x is the amplitude of input and y1 is the amplitude of fundamental harmonic component of input. As we know, we have a number of harmonic components. We will consider here only fundamental harmonic component. So stability analysis using describing function. This stability analysis using describing function is somewhat similar to Nyquist criteria. Here also we use the concept of encirclement and enclosement about the critical point. So first of all, let us take the nonlinearity as a describing function, and it is given to the plant with a unity feedback system, which we are showing in the block diagram. For that one, if we frame a closed loop transfer function, C of S by R of S becomes like this, but here we are changing the transfer function as sinusoidal transfer function, nothing but we are replacing S with j omega. Therefore, C of j omega by R of j omega is equal to kn of x into g of j omega by 1 plus kn of x into g of j omega. Here we need to consider only the characteristic equation. The characteristic equation is 1 plus kn of x g of j omega is equal to 0. From that, g of j omega is equal to minus 1 by kn of x. In the describing function analysis, the classical frequency response analysis is modified so that the entire minus 1 by kn of x locus becomes a locus of critical points. Therefore, for deciding the system stability, here we will use the concept of encirclement and enclosement. Therefore, if the stability can be predicted by using the concept of enclosement. If minus 1 by kn of locus is not enclosed by the g of j omega locus, then the system is stable. Suppose if minus 1 by kn of locus is enclosed by the g of j omega locus, then the system is unstable. Suppose if the minus 1 by kn of x passes through the g of j omega locus at particular points, at those points it will exhibit the sustained oscillations, which we are calling it as limit cycles. This is the entire concept can be explained by using this diagram. Here at the points of A and B it will exhibit the oscillations, and this is the minus 1 by kn x locus enclosed by g of j omega locus, and here it is not enclosed by the locus. So here one is stable region, another one is unstable region, and at these points it exhibits sustained oscillations. So this is the concept of stability in nonlinear control systems. Thank you.